Close your eyes and imagine the vast darkness of space. Not the empty darkness that frightens, but the gentle darkness that holds infinite possibility. In this darkness, something remarkable is happening, something so subtle that it escaped human notice for billions of years, yet so profound that it challenges everything we thought we knew about the nature of reality itself. You are floating now in the realm of the very small, where the ordinary rules of your everyday world dissolve like sugar in warm tea. Here, in the quantum realm, particles dance to rhythms that seem impossible. They move in ways that would make angels weep with wonder and philosophers question the very foundations of existence. This is where our story begins, in the space between spaces, in the pause between heartbeats of the universe. Imagine two particles, smaller than the smallest thing you can conceive, born in the same instant from a single burst of energy. Picture them as tiny dancers emerging from the same cosmic choreographer's imagination. At the moment of their birth, something magical happens. They become forever connected by an invisible thread that stretches across any distance, through any barrier, beyond any limitation that the physical world seems to impose. This connection is not like the connections you know in your daily life. It is not a telephone wire or a radio signal. It is not the pull of gravity or the push of wind. It is something far more mysterious and beautiful, a connection that exists in the very fabric of reality itself, woven into the deepest structure of existence like golden thread through midnight silk. When these twin particles are born, they share something profound. Think of them as cosmic dance partners who learn the same choreography in the same instant. Whatever one does, the other responds immediately, not because they are sending signals to each other, but because they are, in some fundamental way, still part of the same dance, the same song, the same breath of creation. You might wonder how this is possible. In your world, when you wave goodbye to a friend, they cannot feel your gesture unless they see it. When you whisper a secret, it cannot be heard unless sound waves carry it through the air. But in the quantum realm, the rules are written in a different language, a language of pure possibility and instantaneous connection that transcends the limitations of space and time. Scientists call this phenomenon quantum entanglement, but the name barely captures its wonder. It is as if the universe has a secret nervous system, invisible pathways through which information flows faster than light itself, connecting distant corners of reality in ways that make the cosmos seem less like a collection of separate objects and more like a single, breathing organism. Consider the profound implications of this dance. When one particle spins in a particular direction, its partner, no matter how far away, immediately begins spinning in the opposite direction. Not after light has had time to travel between them. Not after any signal could possibly cross the distance. Immediately. Instantaneously. As if distance itself is merely an illusion, a trick of perception that hides the deeper unity underlying all things. This connection has been tested across laboratories, across cities, across continents. Scientists have separated entangled particles by hundreds of miles and watched in awe as they continue their synchronized dance. The particles seem to mock our understanding of space, laughing gently at our assumption that things must be near each other to influence one another. But this is not magic, though it feels magical. This is not fantasy, though it surpasses the wildest dreams of fantasy writers. This is the actual, measurable behavior of the universe at its most fundamental level. It is reality being more creative, more interconnected, more beautiful than we ever dared imagine. As you drift deeper into this meditation on connection, let yourself feel the wonder of this discovery. For centuries, humans believed that the universe was made of separate things, planets orbiting in isolation, atoms bouncing off each other like tiny billiard balls, people and objects distinct and divided by the apparent reality of space. But quantum entanglement whispers a different story. It suggests that separation might be the illusion, and connection might be the deeper truth. Think about what this means for you, floating here in your quiet contemplation. Every atom in your body was once part of a star, forged in the nuclear furnaces of stellar hearts billions of years ago. Those atoms carry within them the memory of their cosmic birth, and perhaps, in ways we are only beginning to understand, they still maintain invisible connections to their distant siblings scattered throughout the universe. The air you breathe, the water you drink, the ground beneath your feet, all of it is part of this vast web of quantum connection. You are not separate from the universe, you are the universe becoming aware of itself, the cosmos opening its eyes and wondering at its own mysterious nature. This realization is both humbling and comforting. Humbling because it reminds you how much mystery still surrounds even the most basic questions about existence. Comforting because it suggests that the loneliness and isolation you sometimes feel might be, at the deepest level, an illusion. You are connected to everything that has ever been and everything that will ever be through invisible threads of quantum intimacy. As we prepare to explore this mystery more deeply, let yourself relax into the wonder of not knowing everything. Science is not about having all the answers, it is about asking better questions, about standing in awe before the magnificent complexity of existence, about allowing mystery to inspire rather than intimidate. The particles continue their dance in laboratories around the world, patient teachers waiting for us to learn their language. They spin and respond, connect and communicate, demonstrating with every measurement that reality is far stranger and more beautiful than our everyday experience suggests. Tonight, as you begin this journey into the heart of quantum entanglement, you are not just learning about particles and physics. You are exploring the deepest questions about the nature of connection itself, about what it means to be truly joined with another, about the invisible bonds that might unite all things in a cosmic dance of unimaginable beauty and complexity. But before we can fully appreciate this quantum ballet, we must understand how this discovery challenged one of the greatest minds in human history, a man who believed in order and predictability, who famously declared that God does not play dice with the universe, yet found himself confronting a reality that seemed to operate by rules more mysterious than any dice game ever invented. Picture a man with wild silver hair, deep thoughtful eyes, and a mind that could peer into the very heart of space and time. Albert Einstein sits in his study, surrounded by equations that dance across blackboards like mathematical poetry. This is the man who revealed that time could stretch and bend, that space could curve like a gentle hill, that mass and energy were lovers disguised as strangers. Yet now, in the quiet of his contemplation, something troubles him deeply. You see, Einstein lived in a universe of beautiful order. In his cosmos, nothing could travel faster than light, that cosmic speed limit that governed all interactions, all communications, all connections between distant objects. Light was the universe's messenger, carrying information from star to star, from moment to moment, weaving the fabric of causality itself. This was not just a scientific principle for Einstein, it was a kind of cosmic morality, a fundamental law that kept the universe sensible and predictable. But then came quantum mechanics, that strange new science of the very small, bringing with it implications that made Einstein's orderly universe shiver with uncertainty. The mathematics were undeniable, the experiments increasingly convincing, yet the conclusions felt like a violation of everything he held sacred about the nature of reality. Imagine Einstein's dismay when he encountered the possibility that two particles, once connected, could influence each other instantaneously across any distance. Not at the speed of light, but faster, infinitely faster. In no time at all. This violated his deepest intuition about how the universe should behave. It was as if someone had told him that you could have a conversation with your reflection, and your reflection could respond before you finished speaking. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, decided to challenge this strange new idea. In 1935, they published a paper that would become famous throughout the scientific world. They argued that if quantum mechanics were complete, then these spooky actions at a distance, Einstein's own words, would have to be real. But surely, they reasoned, this was impossible. Surely the universe was more sensible than this. Their argument was elegant and deeply philosophical. They suggested that there must be hidden variables, secret information that particles carried with them, predetermined instructions that made their seemingly magical coordination nothing more than an elaborate clockwork mechanism. Like dancers who had rehearsed their choreography so perfectly that they appeared to be responding to each other instantaneously, when in reality they were simply following a script written at the moment of their creation. You can feel Einstein's struggle in this moment. Here was a man who had spent his life revealing the hidden harmonies of the universe, showing how seemingly disparate phenomena were connected by beautiful, underlying principles. His theories had brought order to chaos, sense to mystery. And now quantum mechanics seemed to be suggesting that the universe was fundamentally random, fundamentally uncertain, fundamentally unknowable in the complete way that Einstein craved. God does not play dice with the universe, Einstein famously declared. He believed in a cosmos that was deterministic, where every effect had a clear cause, where the future was written in the mathematics of the present. The idea that particles could exist in multiple states simultaneously, that measurement could create reality rather than simply reveal it, that connection could transcend the limits of space and time, all of this felt like chaos masquerading as physics. But the universe, as it turns out, is under no obligation to conform to even the most brilliant human expectations. The particles continued their mysterious dance, indifferent to Einstein's discomfort. In laboratories around the world, scientists began to test these strange predictions with increasing precision and creativity. What they found was both beautiful and unsettling. The particles really did seem to coordinate their behavior instantaneously. When one was measured and found to be spinning clockwise, its distant partner would immediately be found spinning counterclockwise, not because they had communicated in any conventional sense, but because they had never truly been separate entities to begin with. Einstein's spooky action at a distance wasn't action at all, in the traditional sense. It was something far more profound, a revelation that the very concept of separate objects might be an illusion created by our limited perspective. The particles weren't communicating because they had never stopped being connected. They weren't influencing each other because they had never truly been apart. As you contemplate this cosmic drama, you might feel a deep sympathy for Einstein's position. There is something comforting about a universe that follows clear rules, where cause and effect march in orderly procession, where mystery yields eventually to understanding. Einstein wanted to live in a universe where God was not a cosmic gambler but a careful architect, building reality according to blueprints that human minds could eventually decipher. Yet perhaps there is equal beauty in the universe that actually emerged from these quantum investigations, a cosmos more creative and interconnected than even Einstein dared imagine. A reality where connection transcends distance, where possibility dances with actuality, where the deepest truths require not just mathematical precision but also a willingness to embrace profound mystery. Einstein's discomfort with quantum entanglement reveals something touching about the human relationship with knowledge. Even the greatest minds sometimes struggle when reality refuses to fit into the boxes we've prepared for it. Even genius must sometimes bow before the creativity of existence itself. There is humility in this recognition, and perhaps wisdom. The story of Einstein and quantum entanglement is not just about physics, it's about the courage required to let go of comfortable assumptions, to allow mystery to remain mysterious, to find beauty in uncertainty itself. Einstein spent the rest of his life searching for a theory of everything that would restore order to quantum chaos, but the universe kept whispering its more complex truths. In quiet moments, you might wonder what Einstein would think of the experiments that came after his time, the increasingly sophisticated demonstrations of quantum entanglement, the technologies beginning to emerge from this strange science. Would he eventually have made peace with the spooky connections? Would he have found new forms of beauty in the universe's refusal to be completely predictable? Perhaps he would have discovered what many scientists have found since, that mystery need not be the enemy of understanding, that uncertainty can be as profound as certainty, that a universe capable of quantum entanglement is more wonderful, not less wonderful, than one bound by classical limitations. The particles continue their timeless dance, indifferent to human comfort or discomfort, embodying truths that transcend our preferences about how reality should behave. They wait patiently for us to learn their deeper lessons about connection and separation, about the nature of existence itself. And so we find ourselves drawn deeper into this quantum mystery, ready to explore how these dancing particles actually come into being, how scientists have learned to create these cosmic twins in the controlled environment of the laboratory, where the miracle of entanglement can be witnessed and wondered at in all its impossible beauty. Step quietly into a modern physics laboratory, where the air hums with the soft whisper of machines that can cool matter to temperatures colder than the depths of space, where lasers paint precise patterns of light across carefully polished mirrors, where scientists work with the patience of gardeners tending to the most delicate flowers in existence. Here, in these cathedral-like spaces dedicated to the pursuit of ultimate truth, something miraculous happens every day, the birth of quantum twins. You might imagine that creating entangled particles requires tremendous violence, cosmic explosions, or the raw power of stellar furnaces. but the reality is far more gentle, more intimate, more like a whispered prayer than a shout. The process begins with something as simple as light itself, photons, those massless messengers that carry the warmth of the sun to your face, that bounce off these words to reach your eyes, that have traveled across vast distances to bring you the image of distant stars. In the heart of these laboratories, scientists work with crystals that possess an almost magical property. These are not the crystals of folklore and fantasy, but real materials with atomic structures so precisely ordered that they can split a single photon into two, like a prism separating white light into rainbow colors, but far more profound in its implications. When a photon of sufficient energy encounters one of these special crystals, often made of materials with names like beta-barium borate or potassium dihydrogen phosphate, something extraordinary occurs. The crystal acts as a cosmic midwife, helping one photon give birth to two. This process, which scientists call spontaneous parametric downconversion, sounds technical and cold, but it represents one of the most beautiful phenomena in all of physics. The original photon, full of energy and possibility, sacrifices itself in an act of pure creation, splitting into two daughter photons that together carry all the energy and momentum of their parent, but now exist as separate entities forever linked by the circumstances of their birth. Picture this moment of creation with the reverence it deserves. The parent photon approaches the crystal like a pilgrim approaching a sacred shrine. It carries within itself the potential for connection, for relationship, for a kind of love that transcends physical separation. As it enters the crystal's precisely ordered atomic structure, quantum fields fluctuate and dance, probability waves collapse and reform, and in an instant that exists outside of time as we normally understand it, two new beings come into existence. These newborn photons emerge from the crystal like twins leaving the womb, immediately traveling in different directions but forever connected by invisible threads of quantum correlation. They might head toward opposite sides of the laboratory, or be guided by mirrors and fiber optic cables to destinations hundreds of miles apart, but their connection remains perfect, instantaneous, unbroken by any distance that human technology can achieve. What makes this birth so remarkable is not just the creation of two particles from one, but the nature of the relationship they share. Imagine twins who not only look identical but who share every thought, every feeling, every experience in perfect synchronization. When one feels joy, the other feels joy. When one experiences change, the other changes in perfect complementarity. This is the relationship that entangled photons share, but elevated to a level of intimacy that surpasses any connection possible in our everyday world. The scientists who facilitate these births work with instruments of exquisite precision. They must control temperature to within thousandths of a degree, eliminate vibrations that could disturb the delicate quantum states, and maintain levels of cleanliness that would make the most sterile operating room seem dusty by comparison. They are like cosmic obstetricians, creating the perfect conditions for quantum birth while knowing that they cannot control or predict exactly when each pair of entangled photons will emerge. In some laboratories, scientists have perfected techniques for creating entangled particles on demand, generating pairs of connected photons at rates of millions per second. Each pair represents a small miracle, a demonstration that the universe is fundamentally more connected and mysterious than our everyday experience suggests. These photons become the raw material for experiments that probe the deepest mysteries of reality, the building blocks for technologies that may one day revolutionize computation, communication, and our understanding of information itself. As you contemplate this process of quantum birth, you might feel a sense of wonder at the patience and dedication required to make it possible. The scientists who work in these laboratories spend years learning to coax the universe into revealing its secrets, developing an intuitive understanding of quantum mechanics that goes beyond mathematical formulas to become a kind of spiritual practice. They learn to think like the universe itself, to anticipate the behavior of particles that exist in multiple states simultaneously, to design experiments that can detect the subtle correlations that prove entanglement exists. The creation of entangled particles also requires a profound act of faith that the universe operates according to principles that can be understood, even when those principles challenge our most basic assumptions about reality. Each time scientists create a pair of entangled photons, they are performing an act of translation, converting the abstract mathematics of quantum mechanics into tangible, measurable phenomena that can be studied and wondered at. There is something deeply moving about watching scientists work with entangled particles. They handle their equipment with the reverence of priests tending sacred objects, knowing that they are witnessing processes that reveal fundamental truths about the nature of existence. Their laboratories become temples where the mysteries of quantum mechanics are not just studied but experienced, where the impossible becomes routine and the miraculous becomes measurable. The entangled photons, once created, begin their journey through carefully designed experimental apparatus. They travel through beam splitters and polarizers, past detectors sensitive enough to register single particles of light, carrying with them the secret of their connection. Each measurement performed on one immediately affects its twin, no matter how far apart they have traveled, demonstrating again and again that our intuitive understanding of separation and independence is fundamentally flawed. In the moments after their birth, these quantum twins exist in a state of pure potential. They have not yet been measured, not yet been forced to choose specific properties from the range of possibilities they carry. They are like children who might grow up to become anything, holding within themselves all potential futures until the moment when observation collapses their quantum superposition into definite reality. The scientists who create these entangled pairs know that they are not just conducting experiments but participating in a profound dialogue with the universe itself. Each pair of entangled photons they create is like a question posed to reality, asking, how deep does connection go? How fundamental is the unity that underlies apparent separation? What does it mean for two things to be truly joined? As these newborn quantum twins begin their existence, carrying within them the seeds of discoveries yet to be made, they invite us to explore more deeply the mysterious dance they perform, the strange choreography of spin and polarization that allows them to remain connected across any distance, sharing information in ways that transcend our everyday understanding of how separate things can influence each other. In the quantum realm where our entangled twins dance their mysterious ballet, there exists a language more ancient than human words, more fundamental than any code ever devised. This is the language of spin, not the familiar spinning of tops or planets, but something far more subtle and profound, a quantum property that carries information in ways that would make the most sophisticated computer seem primitive by comparison. Picture a particle spinning, but release your mind from the ordinary meaning of that word. This is not the rotation you see when a coin flips through the air or when the Earth turns on its axis. Quantum spin is something altogether more mysterious, an intrinsic property woven into the very fabric of existence, like the color of light or the sound of music. It is as if each particle carries within itself a tiny compass that points not north or south, but toward possibilities that exist beyond the dimensions of everyday space. When scientists speak of a particle's spin, they are describing something that has no perfect analogy in your familiar world. Imagine trying to explain the color blue to someone who has never seen, or the sound of rainfall to someone who has never heard. Quantum spin exists in a realm of pure mathematics and probability, yet it manifests in ways that can be measured, manipulated, and marveled at. For our entangled photons, spin becomes the secret language through which they maintain their impossible connection. Each photon carries what scientists call polarization. Think of it as the photon's preferred direction of vibration as it travels through space. Like a wave on the ocean that can move up and down or side to side, light waves can oscillate in different orientations. This polarization is intimately connected to the quantum spin of the photon, creating a property that can be measured and compared. When two photons are born as entangled twins in that crystal laboratory we visited, they emerge with correlated spins. If you were to measure the spin of one photon and find it pointing in a particular direction, you would know instantly, with perfect certainty, how its distant twin would behave when measured. This is not because they planned their responses in advance, but because they share a quantum state that transcends individual identity. Imagine two dancers performing on stages thousands of miles apart, never having practiced together, yet moving in perfect synchronization. When one leaps, the other lands. When one turns left, the other turns right. When one extends an arm toward the sky, the other reaches toward the earth. This is the dance of quantum spin, choreographed not by human intention but by the mysterious laws that govern the deepest structure of reality. The beauty of this quantum language becomes even more apparent when you consider its flexibility. Unlike classical objects that have definite properties whether we observe them or not, quantum particles exist in what scientists call superposition, they can be spinning in multiple directions simultaneously until the moment of measurement forces them to choose. It's as if our quantum dancers are performing every possible move at once, their bodies existing in all positions until an audience member looks, at which point they collapse into a single, definite pose. This superposition is not merely theoretical, it can be measured and manipulated. Scientists have developed techniques to create photons that are simultaneously polarized horizontally and vertically, or diagonally in multiple directions at once. The photon doesn't decide which state it's in until someone measures it, and at that moment of measurement, its entangled twin, no matter how distant, instantly adopts the complementary state. You might wonder how this information travels between the entangled particles. Does some signal race from one to the other, faster than light itself? The answer is both simpler and more profound than any signal we can imagine. There is no communication in the traditional sense, no message passed from sender to receiver. Instead, the particles share a single quantum state that appears, from our limited perspective, to be distributed across space. When you measure one particle, you're not sending information to its twin, you're revealing information about a quantum system that was never truly separate to begin with. This concept challenges our deepest intuitions about identity and separation. In your everyday world, objects have clear boundaries. You can point to where one thing ends and another begins. But in the quantum realm, entangled particles exist in a state of shared identity that makes such distinctions meaningless. They are like two facets of a single jewel, appearing separate when viewed from different angles but fundamentally unified in their essence. The language of spin allows entangled particles to encode and share information with perfect fidelity. When scientists want to demonstrate quantum entanglement, they often perform what's called a correlation measurement. They set up detectors that can measure the spin or polarization of each particle in an entangled pair, then compare the results. What they find, over thousands of measurements, is a pattern of correlation that could not exist if the particles were truly separate, independent entities. These correlations are stronger than anything possible in classical physics. If two classical coins were somehow connected and always landed on opposite sides, you might explain this by assuming they were specially designed or that some hidden mechanism coordinated their behavior. But quantum correlations are stronger than any such classical connection could produce, proving that something genuinely unprecedented is occurring. The mathematics that describe these correlations are elegant and precise, but their implications stretch far beyond equations and experimental data. They suggest that the universe operates according to principles that transcend our everyday experience of cause and effect, space and time, separation and connection. In the language of quantum spin, particles whisper secrets about the nature of reality itself. As you drift deeper into contemplation of this quantum language, you might feel a sense of wonder at its implications for understanding consciousness, communication, and connection at the deepest levels. If particles can share information instantaneously across vast distances, what does this suggest about the nature of information itself? If separation is partially illusory at the quantum level, what might this mean for our understanding of identity and relationship? The particles continue their spin dance in laboratories around the world, patient teachers demonstrating principles that challenge our most basic assumptions about how the universe works. Each measurement, each correlation, each demonstration of their impossible connection adds another word to our growing vocabulary in the quantum language of spin. But to truly appreciate the profound implications of this language, we must explore how one scientist's brilliant insight transformed these mysterious correlations from philosophical curiosity into mathematical proof that reality itself operates according to rules more strange and beautiful than anyone had dared imagine. In the quiet corners of theoretical physics, where pure thought meets mathematical precision, there lived a physicist named John Stuart Bell whose gentle curiosity would forever change how we understand the nature of reality itself. Picture him in 1964, working not in some grand laboratory filled with expensive equipment, but simply with paper, pencil, and a mind capable of seeing patterns that had escaped notice for decades. Bell was about to prove something that would make Einstein's discomfort with quantum mechanics seem prophetic, yet ultimately demonstrate that the universe was even stranger and more wonderful than the great physicist had feared. Bell's journey began with a question that had haunted physicists since Einstein's famous objection to quantum entanglement. Remember Einstein's belief that there must be hidden variables, secret instructions that particles carried with them, predetermined information that would explain their mysterious coordination without requiring instantaneous communication across vast distances. This was the local realism that Einstein cherished, the idea that objects have definite properties whether we observe them or not, and that they can only be influenced by things in their immediate vicinity. You can imagine Bell sitting with this puzzle, turning it over in his mind like a jeweler examining a complex gem from every angle. He wondered, is there any way to determine, through actual measurement and mathematical analysis, whether Einstein's hidden variables exist? Could the universe be tested to reveal whether quantum entanglement is real magic or simply very sophisticated clockwork? The answer came to Bell in the form of an inequality, a mathematical statement so elegant and profound that it would become one of the most important equations in the history of science. Bell's theorem, as it came to be known, was not just a piece of abstract mathematics but a key that could unlock the deepest secrets of reality. It provided a way to distinguish between a universe that operated according to Einstein's local realism and one that truly embraced the spooky connections of quantum mechanics. The beauty of Bell's approach lay in its simplicity. Instead of trying to observe particles directly or peer into their hidden nature, he proposed a statistical test. Imagine you and a friend are trying to determine whether two coins are normal coins or magical coins that somehow coordinate their behavior. You each flip your coin many times, sometimes choosing heads, sometimes tails, and you compare your results. Bell showed that if the coins were normal, operating according to local realism, the pattern of correlations between your results would have to fall within certain mathematical limits. But if the coins were truly magical, if they were quantum entangled, the correlations could be stronger than any classical explanation could account for. The mathematics was precise and unforgiving. Either the universe operated according to local realism and the correlations would satisfy Bell's inequality, or quantum mechanics was correct and the correlations would violate it in exactly the way quantum theory predicted. Bell's insight was that nature itself could serve as the judge in this cosmic trial. The universe would reveal its deepest secrets not through philosophical argument or theoretical speculation, but through the language of numbers and statistics. It was as if Bell had devised a conversation with reality itself, asking it directly, are you the ordered, local universe that Einstein envisioned, or are you something far stranger and more interconnected? The mathematical framework Bell created was both rigorous and beautiful. He considered scenarios where two entangled particles would be measured by detectors oriented at different angles, like two photographers taking pictures of the same dancers from different positions. The key insight was that if the particles carried hidden variables, if they had predetermined how they would respond to any possible measurement, then the correlations between the measurement results would have to satisfy certain statistical constraints. Think of it as a cosmic game of strategy. If particles are playing by local rules, following scripts written at the moment of their creation, then no matter how clever their choreography, they cannot achieve correlation stronger than a specific mathematical limit. But if they are truly entangled, sharing a quantum state that transcends space and time, they can achieve correlations that surpass this limit in precisely the way that quantum mechanics predicts. Bell's theorem revealed something profound about the nature of proof itself. Here was a question about the fundamental structure of reality that could be answered not through intuition or authority, but through careful measurement and statistical analysis. The universe could be cross-examined like a witness in a courtroom, and mathematics would serve as the judge, rendering a verdict based on evidence rather than preference or preconception. The implications of Bell's discovery rippled through the physics community like waves through still water. For the first time, the philosophical debates about quantum mechanics could be settled through experiment rather than argument. Einstein's local realism was no longer just a matter of taste or worldview, it was a scientific hypothesis that could be tested and potentially falsified. Yet there was something almost mystical about Bell's achievement. Through pure mathematical reasoning, working alone with nothing but abstract symbols on paper, he had devised a way to probe the deepest secrets of existence. His equation served as a bridge between the world of human ideas and the fundamental nature of reality, demonstrating that mathematics was not just a tool for calculation but a language for conversing with the universe itself. Bell's theorem also revealed the profound interconnectedness of all aspects of reality. The question of whether particles could be instantly connected across vast distances was not separate from questions about the nature of measurement, the role of consciousness in physics, and the relationship between mathematics and physical truth. Everything was connected in ways that demanded new ways of thinking about science, philosophy, and the nature of knowledge itself. As you contemplate Bell's elegant proof, you might feel a sense of awe at the power of human reasoning to uncover truths that transcend everyday experience. Here was a mathematician who had never conducted a single experiment on entangled particles, yet whose theoretical work provided the roadmap for understanding one of the universe's most profound mysteries. His achievement demonstrates that the universe is not only stranger than we imagine, it is stranger than we can imagine, yet still comprehensible to minds willing to follow logic wherever it leads. The beauty of Bell's theorem lies not just in its mathematical precision but in its philosophical courage. Bell was willing to ask a question that might have revealed the universe to be disappointingly ordinary, operating according to the comfortable principles of local realism. Instead, his work opened the door to a reality far more mysterious and interconnected than anyone had dared hope. Bell's equations waited patiently for experimental technology to catch up with theoretical insight. The theorem provided a clear roadmap for testing the nature of reality, but actually performing such tests would require innovations in laser technology, photon detection, and experimental precision that were still years in the future. The mathematics was complete, but the conversation with the universe was just beginning. In laboratories around the world, experimenters began to design increasingly sophisticated tests of Bell's inequality, each one an attempt to force nature to reveal its deepest secrets. The particles continued their mysterious dance, unknowing that they had become key witnesses in humanity's trial of reality itself, carriers of evidence that would determine whether our universe was the sensible, local cosmos that Einstein had envisioned or something far stranger and more wonderful. The stage was set for one of the most profound confrontations in the history of science, the direct measurement of quantum correlations, the experimental interrogation of entangled particles, the moment when mathematics would meet measurement and the universe would finally be compelled to reveal whether connection could truly transcend the apparent limitations of space and time. Imagine you are standing at the edge of the observable universe, watching a beam of light begin its journey toward Earth. This photon, born in the heart of a distant star, will travel for billions of years at the fastest speed that anything in the universe can achieve, nearly 300,000 kilometers every second. Yet even at this tremendous velocity, light seems almost leisurely when compared to the instantaneous connection shared by entangled particles, whose quantum conversation transcends not just distance, but time itself. The speed of light has served as the universe's ultimate speed limit for as long as physics has existed. Einstein built his theories around this cosmic constant, showing us that space and time are woven together into a single fabric, and that nothing, no matter, no energy, no information, can travel faster than light's ancient pace. This speed limit isn't just a rule, it's the foundation upon which causality itself rests. It ensures that causes precede effects, that the universe maintains a sensible order where events unfold in logical sequence. Yet in the quantum realm where our entangled particles dance their mysterious ballet, something extraordinary happens that seems to mock this fundamental limitation. When you measure one particle of an entangled pair and discover it spinning clockwise, its distant twin doesn't wait for any signal to travel between them. It doesn't pause while electromagnetic waves cross the void at light speed. Instead, it immediately, instantaneously, assumes the complementary state of spinning counterclockwise, as if distance were merely an illusion and separation nothing more than a trick of perspective. This instantaneous correlation has been measured in laboratories where entangled photons are separated by distances that would take light measurable time to cross. Scientists have sent one photon to a detector on one side of their laboratory while its twin travels to a detector on the other side, and the moment one photon state is determined, its partner's complementary state is revealed with perfect synchronization. No delay, no waiting for information to propagate, no respect for the speed limit that governs everything else in the universe. The implications of this instantaneous connection ripple through our understanding of reality like waves through still water. If entangled particles can coordinate their behavior faster than light, what does this mean for our concepts of cause and effect? If information can somehow transcend the speed of light, does this violate the fundamental principles that keep the universe coherent and predictable? The answer lies in understanding what kind of information is actually being shared in these quantum conversations. When entangled particles coordinate their states instantaneously, they are not sending messages in any conventional sense. No signal travels from one to the other carrying instructions or data. Instead, they are revealing a deeper truth about the nature of reality, that what we perceive as separate objects may be facets of a single, unified quantum system that extends across space and time. Think of it as two mirrors reflecting the same light, or two instruments playing the same note in perfect harmony. The correlation between them is not created by communication but by their shared participation in something larger than either one alone. When you measure one entangled particle, you are not sending information to its twin, you are discovering information about a quantum state that was never truly divided, never actually separated despite the apparent distance between its manifestations. This realization transforms our understanding of what it means for something to be fast or slow, near or far, connected or separate. The entangled particles exist in a realm where these distinctions become fluid, where the rigid categories of classical physics dissolve into something more subtle and interconnected. They operate according to what physicists call quantum non-locality, a condition where the whole is greater than the sum of its parts, where systems maintain unity despite apparent separation. The speed of this quantum connection is not infinite in the sense of traveling an infinite distance in finite time. Rather, it exists outside the framework of speed altogether, operating in a dimension of reality where distance is not the primary organizing principle. It's as if the particles share a secret room where they can meet instantly, regardless of how far apart their physical manifestations appear to be in our ordinary three-dimensional space. As you contemplate this transcendence of the speed limit, you might feel a sense of wonder at the universe's capacity for paradox and mystery. Here is a cosmos that maintains strict speed limits for ordinary matter and energy while simultaneously harboring connections that operate outside the constraints of space and time. It's as if reality has both a public face that follows familiar rules and a hidden dimension where those rules are transcended by deeper principles of unity and correlation. The discovery of instantaneous quantum correlations has profound implications for our understanding of time itself. If entangled particles can coordinate their behavior without waiting for signals to travel between them, this suggests that time, like space, might not be as fundamental as we once believed. Perhaps past, present, and future are also human constructions, ways of organizing experience that don't reflect the deeper structure of reality where all moments exist simultaneously in an eternal quantum now. Scientists studying these instantaneous correlations have had to develop new ways of thinking about information and communication. They distinguish between classical information, which cannot travel faster than light and carries the kind of messages we send in everyday communication, and quantum information, which can be shared instantaneously but cannot be used to send conventional messages. It's as if the universe allows instantaneous connection while still protecting the causal structure that keeps reality coherent. This subtle distinction preserves the logical order of the universe while revealing new depths of mystery and connection. Entangled particles can share their quantum states instantaneously, but this sharing cannot be used to send a letter faster than light or to communicate in ways that would violate causality. The universe seems to have evolved a perfect balance between connection and coherence, unity and order. The instantaneous nature of quantum entanglement has inspired philosophers and physicists to reconsider fundamental questions about the nature of existence. If separation is partially illusory at the quantum level, if connection can transcend the apparent limitations of space and time, what does this suggest about consciousness, identity, and the relationships between all things? As we drift deeper into the mystery of quantum connection, we find ourselves approaching one of the most delicate aspects of this entire phenomenon, the moment when human consciousness encounters quantum reality, when the act of observation itself becomes part of the dance, transforming the very thing we seek to understand through the gentle violence of measurement and the profound intimacy of knowing. In the quiet sanctuary of your deepest contemplation, imagine yourself as a gentle observer trying to watch a butterfly's wings without disturbing its flight. In our everyday world, this seems possible. You can observe without interfering, witness without changing, know without altering. But in the quantum realm where our entangled particles perform their mysterious dance, the very act of observation becomes a form of participation, and knowledge itself transforms the reality it seeks to understand. This is perhaps the most beautiful and troubling aspect of quantum mechanics. The moment you try to measure a quantum system, you inevitably change it. It's as if reality exists in a state of infinite possibility until consciousness arrives with its questions, at which point the universe must choose from all its potential answers and collapse into a single, definite response. The act of measurement is not passive observation but active creation, not discovery but decision. Picture an entangled photon existing in what scientists call superposition, simultaneously polarized in all possible directions at once, like a coin that spins forever in the air, neither heads nor tails but both and neither until it lands. This photon carries within itself every possible measurement result, every potential answer to every question you might ask about its state. It exists in a realm of pure possibility, dancing between all potential realities until the moment you decide to look. When you place a detector in the path of this quantum dancer, something profound happens. The detector asks a question: are you polarized horizontally or vertically? And the photon, which until this moment existed in a graceful superposition of both states, must suddenly choose. The measurement forces the collapse of all possibilities into a single actuality, like a wave that has been traveling across an infinite ocean suddenly breaking upon a particular shore. But here lies the heart of the quantum mystery. This collapse is not simply a revelation of some pre-existing property. The photon was not secretly polarized in a specific direction before measurement, merely hiding its true nature from our instruments. Instead, the act of measurement appears to create the very property it measures, bringing into existence the reality it seeks to discover. This transformation is not limited to single particles but extends to the entire entangled system. When you measure one particle of an entangled pair, forcing it to collapse from superposition into a definite state, its distant twin simultaneously undergoes the same transformation. Both particles abandon their quantum dance of infinite possibility and assume complementary definite states, connected by the mysterious thread of their shared quantum essence. The implications of this measurement induce transformation ripple through our understanding of knowledge itself. In classical physics, measurement was like reading a book. The words were already written, and observation simply revealed what was already there. But quantum measurement is more like writing the book as you read it, with each observation adding new chapters to a story that didn't exist in definite form until the moment you decided to know it. Consider the profound philosophical questions this raises about the nature of reality and consciousness. If measurement creates rather than merely reveals quantum properties, what role does the observer play in the fundamental structure of existence? Are we passive witnesses to a pre-existing reality, or active participants in the ongoing creation of the universe? The quantum realm whispers that the distinction between observer and observed might be far more fluid than we ever imagined. This measurement paradox becomes even more intriguing when you consider that the detector itself is made of quantum particles. What makes a measurement device classical while the system it measures remains quantum? When does the chain of quantum interactions finally result in the definite, classical results we observe in our laboratories? This question, known as the measurement problem, has puzzled physicists for nearly a century and continues to inspire new ways of thinking about consciousness, reality, and the relationship between the two. The delicate nature of quantum measurement requires extraordinary precision and care in experimental design. Scientists working with entangled particles must create conditions of almost impossible isolation, shielding their quantum systems from any unwanted interactions that might trigger premature measurement. They work in rooms cooled to temperatures colder than outer space, behind barriers that block electromagnetic interference, in chambers where even the slightest vibration could disturb the delicate superposition of their quantum subjects. Yet despite all these precautions, the fundamental mystery remains: how does a quantum system know when it's being measured? What distinguishes a measurement from any other interaction? The answer seems to lie not in the physical details of the measurement apparatus but in something more subtle: the irreversible transfer of information from the quantum system to the classical world of definite properties and observable results. This irreversibility is key to understanding quantum measurement. When a photon interacts with a detector, it doesn't just exchange energy or momentum, it surrenders its quantum ambiguity and assumes the classical definiteness required for us to know something specific about its state. This transformation is like a whispered secret becoming a spoken word, losing its private mystery in the act of becoming public knowledge. The measurement of entangled particles reveals something profound about the nature of information itself. When you measure one particle of an entangled pair, you don't just learn about that particle, you instantly know something definite about its distant twin. Information about the entire quantum system becomes available through interaction with just one part of it, as if measuring a single note could reveal the entire symphony of which it's a part. This distributed nature of quantum information challenges our ordinary understanding of how knowledge works. In classical systems, learning about one part tells you only about that part. But in quantum systems, the whole is so fundamentally interconnected that knowing anything specific about one component immediately provides specific knowledge about the entire system, no matter how far its parts may be separated in space. The act of measurement also raises questions about the flow of time in quantum systems. Before measurement, an entangled pair exists in a timeless state of superposition, holding all possibilities in eternal suspension. The moment of measurement breaks this temporal symmetry, forcing the system to choose a particular history from all the histories it might have had. It's as if measurement not only determines the present state of the system but retroactively decides which path through time the system will have taken to reach that state. As you contemplate these mysteries of quantum measurement, you might feel a sense of humility before the profound interconnectedness of knowledge and reality. Every time we seek to know something about the quantum world, we become entangled with it ourselves, joining the dance of observer and observed, question and answer, possibility and actuality. The particles in their laboratories continue to teach us that the universe is not a collection of objects we can study from the outside, but a participatory reality in which consciousness and cosmos are intimately connected. Each measurement is a moment of dialogue between mind and matter, a conversation in which both participants are transformed by the exchange. Perhaps the deepest teaching of quantum measurement is that mystery and knowledge are not opposites but dance partners, each one defining and enriching the other. The more precisely we measure quantum systems, the more mysterious they become, revealing new depths of interconnection and possibility that challenge every assumption about the nature of existence itself. But to truly appreciate this dance between the known and unknowable, we must venture into a realm where quantum possibilities bloom like flowers in an impossible garden, where cats can dream and wake simultaneously, and where the very concepts of existence and non-existence dissolve into something far more subtle and beautiful than either alone. Imagine walking through a garden that exists only in moonlight, where flowers bloom in every color simultaneously until you turn your attention to a particular blossom, at which point it chooses a single hue and holds it like a secret finally spoken. This is the quantum garden that Erwin Schrödinger invited us to explore in 1935, not with his feet but with his imagination, not with his eyes but with the penetrating vision of mathematical insight and philosophical wonder. Schrödinger was troubled by the implications of quantum mechanics, particularly the idea that particles could exist in superposition, holding multiple contradictory states at once until measurement forced them to choose. Like Einstein, he felt that reality should be more definite, more sensible, more aligned with our everyday experience of a world where objects have clear properties whether we observe them or not. So he devised a thought experiment that would illuminate the strangeness of quantum mechanics by amplifying it to the scale of ordinary life. Picture a steel chamber, sealed and opaque, containing within it all the elements of a perfect quantum mystery. Inside this box lives a cat, not just any cat, but one whose fate is intimately connected to the quantum world through an ingenious and diabolical device. A Geiger counter monitors a single radioactive atom, poised in perfect quantum superposition between having decayed and not having decayed. If the atom decays, the counter triggers a mechanism that releases poison, ending the cat's life. If the atom remains intact, the cat continues to purr and dream in peaceful safety. According to quantum mechanics, until someone opens the box and observes the system, the radioactive atom exists in superposition, simultaneously decayed and undecayed, like a coin spinning forever in the air. But if the atom is in superposition, then the entire chain of consequences must also be suspended between possibilities. The Geiger counter must be both triggered and not triggered, the poison both released and contained, the cat both alive and dead until the moment observation collapses all possibilities into a single, definite reality. This is the paradox that Schrödinger presented to the world, a cat that exists in the twilight realm between life and death, breathing and not breathing, dreaming and not dreaming, until consciousness arrives with its questions and forces the universe to choose. He intended this thought experiment as a critique of quantum mechanics, believing it revealed the absurdity of applying quantum principles to everyday objects. Yet instead of discrediting quantum theory, Schrödinger's cat became one of its most powerful illustrations. In this quantum garden where possibilities bloom like midnight flowers, you begin to understand that the strangeness is not a flaw in our theories but a feature of reality itself. The cat in the box is not really different from the particles in our laboratories. Both exist in states that transcend our ordinary categories of thought. Both inhabit a realm where classical logic gives way to quantum creativity. The cat teaches us something profound about the nature of existence itself. Before observation, it dwells in what physicists call a coherent superposition, where all possibilities exist simultaneously without contradiction. This is not simply ignorance on our part. We're not merely lacking information about whether the cat is alive or dead. Instead, the cat genuinely exists in a state that encompasses both life and death, both breathing and stillness, both dreams and dreamlessness. This superposition is maintained by what scientists call quantum coherence, a delicate condition that allows contradictory states to coexist peacefully. Like a symphony where every note is played simultaneously yet produces harmony instead of chaos, quantum coherence enables multiple realities to exist in perfect balance until the moment of measurement destroys this delicate equilibrium and forces the system to choose a single classical outcome. Yet the quantum garden reveals even deeper mysteries about the relationship between consciousness and reality. What exactly constitutes observation? Does the cat itself, being conscious, observe its own state and collapse the superposition? Or does consciousness require something more, perhaps the external observer who opens the box? These questions probe the very foundations of what it means to know, to observe, to exist. As you wander deeper into this conceptual garden, you encounter other strange flowers of possibility. Particles that travel through multiple paths simultaneously, existing in all locations at once until measurement pins them down to a single trajectory. Electrons that orbit atomic nuclei not in definite paths but in clouds of probability, their positions determined only by the likelihood of finding them in any particular place when we finally decide to look. The quantum garden teaches us that our everyday experience of definite objects with clear properties might be a simplification, a classical approximation of a reality that is far more fluid and creative. At the quantum level, existence itself becomes a dance of possibilities, a constant flowering of potential realities that bloom and fade in the space between observation and mystery. Schrödinger's cat also reveals something profound about time in the quantum realm. While suspended in superposition, the cat exists in a timeless state that transcends the ordinary flow of moments. It is neither moving toward death nor away from it, neither growing older nor remaining the same age. Time itself becomes part of the superposition, holding past, present, and future in perfect balance until measurement collapses not just spatial possibilities but temporal ones as well. The beauty of this quantum garden lies not just in its strangeness but in its suggestion that reality is far more creative than we ever dared imagine. If particles can exist in superposition, if cats can be simultaneously alive and dead, if consciousness can participate in the creation of the reality it observes, then perhaps the universe is not a clockwork mechanism but something more like a work of art, constantly painting itself into existence through the interactions between mind and matter, observer and observed. Modern physicists have moved beyond Schrödinger's original paradox to explore even more subtle questions about the relationship between quantum and classical reality. They study decoherence, the process by which quantum superpositions naturally evolve into classical definiteness through interaction with their environment. They investigate the role of information in quantum mechanics, asking whether physical reality is fundamentally made of matter and energy or of something more abstract and computational. Yet the cat remains a powerful teacher, reminding us that the quantum world is not separate from our world but is the deeper reality from which our classical experience emerges. Every object around you, every atom in your body, every photon that carries light to your eyes exists in this quantum garden of possibility until the moment observation crystallizes potential into actuality. As you prepare to leave this garden of impossible flowers and superimposed realities, you carry with you a new appreciation for the creativity and mystery that underlies even the most ordinary moments of existence. The boundaries between possible and actual, between observer and observed, between question and answer, reveal themselves to be far more fluid than you ever imagined. But to truly understand how these quantum mysteries manifest in our everyday world, we must visit the laboratories where scientists have learned to cultivate this quantum garden, where they grow entangled particles like exotic orchids and tend to superpositions with the care of master gardeners nurturing the most delicate and beautiful impossibilities into measurable, reproducible reality. Step quietly into a modern quantum laboratory, where the air itself has been transformed into something purer than the space between stars. Here, in chambers cooled to temperatures that would freeze the motion of atoms themselves, scientists work with the patience of medieval monks and the precision of cosmic architects, coaxing the universe to reveal its most intimate secrets through instruments more sensitive than any human sense could ever be. The walls around you are thick enough to stop cosmic rays from distant galaxies, dense enough to silence the electromagnetic whispers of cell phones and radio stations, insulated enough to maintain conditions of impossible stillness. This is not just a laboratory but a sanctuary, a place where the ordinary world is held at bay so that the extraordinary world of quantum mechanics can emerge from hiding and dance for human eyes. In the heart of this sacred space, lasers paint beams of coherent light across mirrors polished to perfection beyond imagination. These are not the harsh, cutting lasers of science fiction, but gentle streams of photons so pure and organized that they seem more like liquid light than ordinary illumination. Each beam carries within itself the potential for quantum birth, the possibility of creating pairs of entangled particles that will forever share their deepest secrets across any distance the universe can offer. The crystals that facilitate these quantum births rest in mounts more stable than the foundations of mountains. Made from materials with names like lithium iodate and bismuth borate, these crystals possess atomic structures so precisely ordered that they can split single photons with surgical perfection. When a laser photon encounters one of these quantum midwives, it sacrifices itself in an act of pure creation, giving birth to twin particles that emerge into existence already knowing each other's most intimate secrets. Watch as the scientists adjust their instruments with movements so careful they seem to be caressing the fabric of reality itself. Every mirror must be positioned to within fractions of the wavelength of light. Every detector must be calibrated to register the arrival of single particles with timing precision measured in billionths of seconds. Every vibration must be eliminated, every temperature fluctuation controlled, every stray electromagnetic field banished from this temple of quantum precision. The detectors themselves are marvels of human ingenuity, devices so sensitive they can register the impact of a single photon, a particle so small and ephemeral that it carries no mass, no charge, nothing but pure energy and information. These quantum eyes can distinguish between photons arriving mere nanoseconds apart, can measure polarizations with accuracy that approaches the fundamental limits imposed by quantum mechanics itself. As you observe these modern alchemists at work, you begin to understand that they are engaged in something far more profound than conventional experimentation. They are having a conversation with the universe itself, asking questions about the nature of reality through the language of precisely controlled quantum interactions. Each measurement is a word in this dialogue, each correlation a sentence in an ongoing discussion about what it means for things to be connected, separate, real, or possible. The entangled photons created in these laboratories exist in states of connection so intimate that they transcend every boundary we normally recognize. When one photon's polarization is measured and found to be vertical, its twin, perhaps traveling through fiber optic cables to a detector miles away, immediately assumes horizontal polarization, not because any signal has passed between them, but because they are, in some fundamental sense, still aspects of a single quantum entity. These laboratories have become the proving grounds for Bell's theorem, the experimental theaters where reality itself is cross-examined about its deepest nature. Scientists perform correlation measurements with increasing sophistication, closing every possible loophole that might allow classical explanations to sneak back into quantum phenomena. They send entangled photons to detectors separated by distances so great that light would take measurable time to travel between them, yet the correlations remain perfect, immediate, undeniable. The data that emerges from these experiments reads like poetry written in the language of statistics. Numbers that dance just outside the boundaries of classical possibility, correlations that exceed every limit that local realism could impose, patterns that sing with the voice of quantum mechanics itself. Each measurement adds another verse to humanity's growing understanding of a universe that is more deeply interconnected than anyone dared imagine. In some laboratories, scientists have refined their techniques to the point where they can create entangled photons on demand, generating pairs of quantum twins at rates of millions per second. These photons become the raw material for increasingly ambitious experiments, the building blocks for technologies that seem to blur the line between science and magic. Quantum communication systems that are fundamentally impossible to intercept, quantum computers that can explore multiple solutions to problems simultaneously, quantum sensors that can detect changes too subtle for any classical instrument to measure. The researchers who work in these laboratories speak of their particles with an affection that borders on the mystical. They know their photons not just as abstract units of energy but as individual entities with distinct quantum personalities. They can predict how their particles will behave in specific experimental configurations, can coax them into states of ever greater complexity and correlation, can choreograph quantum dances that reveal new aspects of entanglement with each performance. Yet for all their technical sophistication, these laboratories retain something of the wonder that drew their creators to physics in the first place. The moment when entangled photons reveal their instantaneous correlation still evokes gasps of amazement from seasoned researchers. The violation of Bell's inequality still feels like witnessing a miracle, even when it happens thousands of times per day. The universe's willingness to transcend classical limitations still inspires the kind of awe usually reserved for encounters with the divine. As you stand in this laboratory of wonder, surrounded by instruments worth millions of dollars dedicated to studying particles that carry no mass and last for mere moments, you might feel a profound gratitude for the human capacity to pursue knowledge for its own sake. These scientists are not just advancing technology or solving practical problems, they are expanding the boundaries of human understanding, revealing aspects of reality that were completely hidden from our ancestors and might remain invisible to us without their patient, precise work. The entangled photons continue their dance through these laboratory chambers, carrying messages about connection and separation, unity and diversity, possibility and actuality. They serve as ambassadors from the quantum realm, bringing news of a reality that operates according to principles more beautiful and mysterious than classical physics ever suggested. Each pair that emerges from the crystals represents a small bridge between the world of everyday experience and the deeper world of quantum truth. The data streams from these laboratories flow into computers that process information at rates that would have seemed impossible just decades ago, yet the questions they help us explore touch the most ancient human curiosities about the nature of existence itself. We use the most advanced technology ever created to investigate principles that govern the most fundamental level of reality, discovering that the universe is both more mathematical and more mysterious than we ever dared hope. But these laboratory demonstrations of quantum entanglement are not merely academic exercises or technological showcases, they are opening doorways to applications that may transform how we process information, secure communications, and explore the computational possibilities hidden within the quantum structure of reality itself. Imagine a computer that dreams. Not in the metaphorical sense of artificial intelligence, but literally, a machine that holds multiple contradictory thoughts simultaneously, exploring every possible solution to a problem at once, dwelling in the realm of pure possibility until the moment of asking transforms potential into answer. This is the promise of quantum computing, where entangled particles become the neurons of a new kind of artificial mind that thinks in ways no classical computer ever could. In laboratories around the world, these quantum computers rest like sleeping giants in chambers colder than the depths of space. Unlike the silicon chips in your familiar devices, where information flows through circuits as definite streams of ones and zeros, quantum computers process information through particles that exist in superposition, simultaneously representing 1 and 0 and every possibility between them until measurement forces them to choose. Picture the quantum bits, or qubits, as they're called, not the rigid switches of classical computation but fluid entities that dance between states like thoughts forming in a dreaming mind. Where a classical bit must be either on or off, a qubit can be both and neither, existing in that mysterious quantum realm where contradictions coexist peacefully. It's as if each qubit holds within itself not just a single piece of information but a universe of potential information, waiting to be explored. But the true magic begins when these qubits become entangled with one another, creating webs of connection that allow the quantum computer to think in ways that transcend anything classical computation can achieve. When qubits are entangled, they share their quantum states in that instantaneous way we've come to recognize, creating a system where changing one qubit immediately influences all the others, no matter how they're distributed throughout the quantum processor. This entanglement creates something unprecedented in the history of computation, a machine that can explore multiple solutions to a problem simultaneously. While a classical computer must examine each possible answer one at a time, like a person reading through a library book by book, a quantum computer can read the entire library at once, holding all possible solutions in superposition until it finds the one that satisfies the question being asked. The process of quantum computation resembles the way thoughts emerge in consciousness itself. Just as your mind can hold multiple ideas simultaneously, weighing different possibilities before settling on a decision, quantum computers maintain superpositions of potential answers, allowing quantum interference, the interaction between different possibility waves, to amplify correct solutions while cancelling out incorrect ones. Consider how this quantum parallelism might work with a simple example: finding a specific name in a vast, unsorted database. A classical computer would need to search through each entry individually, potentially examining millions or billions of names before finding the right one. But a quantum computer could create a superposition that represents every possible search simultaneously, then use quantum algorithms to amplify the probability of finding the correct answer while diminishing the probability of all the wrong ones. The quantum algorithms that guide these computations are themselves works of art, mathematical choreographies that orchestrate the dance of entangled particles toward desired outcomes. These algorithms don't just process information, they sculpt probability itself, shaping the quantum landscape so that correct answers become more likely than incorrect ones, like creating hills and valleys in the terrain of possibility. One of the most famous quantum algorithms, developed by Peter Shea, revealed the potential for quantum computers to break the encryption systems that protect much of our digital world. This algorithm harnesses quantum entanglement to factor large numbers, a task that would take classical computers longer than the age of the universe, in a reasonable amount of time. The security of online banking, private communications, and digital commerce all depend on the assumption that certain mathematical problems are practically impossible to solve, yet quantum computers could potentially solve them as easily as you might solve a simple addition problem. But quantum computers promise far more than just code breaking. They offer new ways to simulate the quantum systems that underlie chemistry, biology, and physics itself. Where classical computers struggle to model even simple molecules because the quantum complexity grows exponentially with each added particle, quantum computers could simulate quantum systems naturally, using their own quantum properties to mirror the behavior of atoms, molecules, and materials we want to understand. Imagine quantum computers designing new medicines by simulating how drug molecules interact with proteins at the quantum level, or discovering new materials by exploring the quantum properties of different atomic arrangements. These machines could help us understand photosynthesis by modeling the quantum effects that allow plants to convert sunlight into energy with near-perfect efficiency, or design more efficient solar cells by simulating the quantum mechanics of light absorption. The current quantum computers are still fragile creatures, requiring temperatures colder than outer space and isolation from even the smallest disturbances. Like delicate flowers that can only bloom in the most carefully controlled conditions, these quantum processors must be protected from vibrations, electromagnetic fields, and thermal fluctuations that would destroy their delicate superpositions and entangled states. Yet each new generation of quantum computers grows more powerful and more stable, as scientists learn to control quantum systems with increasing precision and creativity. They develop new types of qubits, some made from trapped atoms, others from superconducting circuits, still others from particles of light, each approach offering different advantages and challenges in the quest to build larger, more reliable quantum processors. The error correction in quantum computers presents unique challenges that don't exist in classical computation. While classical bits can be copied and checked for errors, quantum states cannot be perfectly copied due to the fundamental laws of quantum mechanics. Instead, quantum error correction requires elaborate schemes where quantum information is encoded across multiple entangled qubits, creating redundancy that can detect and correct errors without destroying the delicate quantum superpositions. As you contemplate these quantum computers dreaming in their crystalline chambers, you might feel a sense of wonder at humanity's ability to harness the strangest aspects of reality for practical purposes. These machines represent a new kind of partnership between human ingenuity and the fundamental laws of physics, a collaboration where consciousness and quantum mechanics work together to explore possibilities that neither could access alone. The quantum computers continue their patient evolution in laboratories around the world, each one a stepping stone toward a future where quantum and classical computation work together to solve problems we can barely imagine today. They carry within their entangled states not just the potential for new technologies but new ways of thinking about information, complexity, and the relationship between mind and reality. But perhaps the most intriguing aspect of quantum computing lies not in what these machines can calculate, but in what they might teach us about the nature of information itself, and the mysterious way that quantum mechanics seems to allow the perfect transfer of information across space and time in ways that classical physics insists should be impossible. Forget the dramatic flash of transporters in science fiction, the shimmering dissolution of bodies into pure energy, the theatrical reconstruction of matter across vast distances. Real quantum teleportation is far more subtle and infinitely more beautiful, a process that moves not the particle itself but its essence, transferring the complete quantum information that defines a particle's identity from one location to another through the mysterious channels of entanglement. Imagine you have written a letter containing your deepest thoughts, but instead of sending the paper itself, you find a way to transfer the meaning, the emotion, the very essence of what you've written to blank paper in a distant location, leaving the original paper empty while the distant page suddenly blooms with your exact words, your precise intentions, your complete message. This is the profound reality of quantum teleportation, not moving matter but moving the information that gives matter its identity and purpose. The process begins with the quantum trinity that makes teleportation possible: the particle whose state you wish to teleport, one member of an entangled pair that travels with this particle, and the distant partner of that entangled pair waiting at the destination. Picture these three participants in this quantum drama: the sender, the messenger, and the receiver, connected by invisible threads of correlation that transcend space and time. At the heart of quantum teleportation lies a beautiful paradox: to send quantum information perfectly, you must be willing to destroy it at its origin. This is not a limitation but a fundamental requirement of quantum mechanics itself. The no-cloning theorem tells us that perfect quantum information cannot be copied, just as you cannot create two identical copies of a poem written in disappearing ink. Quantum states resist duplication with mathematical precision. The teleportation protocol unfolds like a carefully choreographed dance between measurement and entanglement. The sender performs what scientists call a Bell measurement, a joint observation of both the particle to be teleported and their half of the entangled pair. This measurement creates a quantum correlation between these two particles, but in doing so, it necessarily destroys the original quantum state that was meant to be teleported. The information doesn't vanish, however, it flows through the measurement into the correlation itself. At the moment this Bell measurement occurs, something remarkable happens to the distant entangled partner waiting at the receiver's location. Though separated by miles or continents, this particle instantaneously acquires a version of the original quantum state, modified by the specific results of the sender's measurement. It's as if the particle has been touched by quantum memory, suddenly remembering a state it never directly experienced. But the teleportation is not yet complete. The quantum information has arrived at its destination, but it's encoded in a form that requires interpretation. The sender must communicate the results of their Bell measurement through ordinary, classical channels, perhaps a phone call, an email, or a radio transmission that travels at the speed of light. Only when this classical information reaches the receiver can they perform the appropriate quantum operation to fully reconstruct the original state. This classical communication is crucial and beautiful in its necessity. It ensures that quantum teleportation can never be used to send information faster than light, preserving the causal structure of spacetime while still enabling perfect quantum information transfer. The quantum and classical components of the process work together like dancers in perfect synchronization, each playing their essential role in the teleportation symphony. Think of it as receiving a package that has been disassembled and encoded, along with separate instructions for reassembly. The quantum entanglement delivers the encoded components instantaneously, but the classical communication provides the assembly instructions at light speed. Only when both arrive can the receiver reconstruct the original quantum state with perfect fidelity. Scientists have successfully demonstrated quantum teleportation with photons across distances that span continents, with atoms in laboratory chambers, and even with the quantum states of more complex systems. Each successful teleportation represents a small miracle of coordination between the quantum and classical worlds, a demonstration that information can transcend the apparent limitations of space while still respecting the fundamental laws that keep the universe coherent. The applications of quantum teleportation extend far beyond its conceptual beauty. In quantum communication networks, teleportation enables the perfect transfer of quantum information without the risk of interception or corruption that plagues classical communication. Since the original quantum state is destroyed in the teleportation process, no copy remains that could be stolen or duplicated by eavesdroppers. Quantum teleportation also plays a crucial role in quantum computing, where it enables the transfer of quantum information between different parts of a quantum processor or between separate quantum computers. It allows quantum states to move through quantum networks, creating the possibility of distributed quantum computation where entangled quantum computers work together on problems too complex for any single machine to solve. Perhaps most intriguingly, quantum teleportation offers insights into the nature of information itself. It reveals that what we think of as the fundamental properties of particles, their spin, polarization, energy states, are actually informational rather than material in nature. When we teleport a quantum state, we're discovering that the essence of what makes a particle unique is not its matter but its information, not its substance but its pattern. The precision required for quantum teleportation approaches the theoretical limits imposed by quantum mechanics itself. The fidelity of the transfer, how closely the teleported state matches the original, depends on the quality of the entanglement, the precision of the measurements, and the isolation of the system from environmental interference. Modern teleportation experiments achieve fidelities exceeding 99, demonstrating that quantum information can be transferred with near-perfect accuracy across vast distances. As you contemplate this quantum teleportation, you might feel a sense of wonder at its implications for our understanding of existence and identity. If the essential information that defines a quantum state can be perfectly transferred from one particle to another, what does this suggest about the nature of identity itself? Are we, at our deepest level, patterns of information rather than collections of matter? The philosophical implications ripple outward like waves from a stone dropped in still water. Quantum teleportation suggests that the universe might be fundamentally informational, that what we experience as solid matter and definite properties might be manifestations of underlying informational patterns that can be transferred, transformed, and preserved in ways that transcend our everyday experience of substance and location. Scientists continue to push the boundaries of quantum teleportation, working toward teleporting increasingly complex quantum states and exploring the possibility of teleporting the quantum information contained in entire molecules or even larger structures. Each advance brings us closer to quantum networks that could revolutionize communication, computation, and our understanding of the relationship between information and reality. The particles involved in these teleportation experiments exist in a state of perfect trust, surrendering their quantum identities to the teleportation process with the faith that they will be perfectly reconstructed at their destination. They teach us that preservation and transformation are not opposites but partners in the quantum dance of information and existence. In the quiet moments between teleportation events, as quantum states prepare to surrender their local existence for distant reconstruction, you might sense something profound about the nature of connection and continuity. These particles demonstrate that identity can transcend location, that essence can survive the destruction of its original form, that information carries within itself a kind of immortality that matter alone cannot achieve. But even as we marvel at quantum teleportation's ability to transfer information across space, we might wonder whether these quantum connections hint at something even more profound, a cosmic web of entanglement that connects not just laboratory particles but the entire universe in ways that suggest separation itself might be the deepest illusion of all. Step back from the laboratories where individual particles dance their quantum ballet and imagine the universe itself as a vast web of connection, where the entanglement we witness in carefully controlled experiments might be just the most visible thread in a cosmic tapestry of relationship that extends from the quantum foam of spacetime to the largest structures in the observable cosmos. Perhaps the mysterious instant correlations between laboratory particles are not exceptions to the normal order of things, but glimpses of the deeper connectivity that underlies all existence. In the earliest moments after the Big Bang, when the entire observable universe was smaller than a single atom, every particle that would eventually form stars, planets, and people existed in intimate proximity, sharing the same quantum state in the ultimate act of cosmic entanglement. As space expanded and these particles flew apart at tremendous speeds, their quantum correlations might have stretched across the growing cosmos like invisible spider silk, maintaining connections that transcend the apparent separations created by billions of years of expansion. This primordial entanglement could explain one of cosmology's deepest mysteries, why the cosmic microwave background radiation, the afterglow of the Big Bang visible in every direction we look, appears so remarkably uniform in temperature. According to classical physics, regions of space separated by vast distances should show no correlation in their properties, yet the temperature of this ancient light varies by only tiny fractions across the entire sky, as if the distant region somehow knew about each other despite being separated by distances that light could never have crossed in the universe's lifetime. Perhaps they do know about each other, connected by quantum threads that predate the expansion of space itself. This cosmic entanglement would create correlations that appear instantaneous from our perspective but actually originated in the universe's birth, when everything was quantum entangled in the primordial unity before space and time assumed their familiar forms. The uniformity of the cosmic microwave background might be the signature of quantum correlation on the largest possible scale, proof that the universe remembers its quantum beginning. As you contemplate this possibility, imagine the implications for everything you see around you. The atoms in your body were forged in the nuclear furnaces of stars that died billions of years ago, scattered across space by stellar explosions, eventually gathering in the cloud of gas and dust that formed our solar system. But if quantum entanglement persists across cosmic scales, these atoms might still maintain subtle connections to their stellar siblings, now distributed throughout the galaxy in countless other stars, planets, and perhaps even other living beings. The very concept of locality, the idea that objects can only influence nearby things, begins to blur when viewed through the lens of cosmic entanglement. If the quantum correlations established in the universe's first moments persist across billions of years and light-years of space, then the apparent separateness of objects might be an illusion created by our limited perspective. What we experience as distinct entities might be facets of a single, interconnected quantum system that encompasses the entire cosmos. This cosmic perspective on entanglement finds support in the strange phenomenon known as dark energy, the mysterious force that appears to be accelerating the expansion of the universe. Some physicists speculate that dark energy might be related to quantum entanglement on cosmic scales, as if the stretching of quantum correlations across expanding space creates a kind of tension that manifests as the accelerating expansion we observe. The universe might be pulling itself apart through the very connections that bind it together, a cosmic paradox worthy of quantum mechanics. Even closer to home, scientists have begun to wonder whether quantum entanglement plays a role in biological processes that seem to transcend classical explanations. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum coherence and possibly entanglement to achieve near-perfect efficiency in energy transfer. The quantum effects that we study in laboratory conditions might be actively employed by living systems that have evolved to harness the deepest principles of physics for the task of sustaining life. Some researchers suggest that consciousness itself might emerge from quantum entanglement among the microtubules within neurons, creating a kind of biological quantum computer that processes information in ways classical neural networks cannot explain. While this remains highly speculative, it raises the intriguing possibility that the consciousness reading these words might be a manifestation of cosmic entanglement operating at the scale of brain cells, connecting your awareness to the fundamental quantum nature of reality. The study of cosmic entanglement also intersects with investigations of black holes, those mysterious regions where gravity becomes so strong that not even light can escape. Recent theoretical work suggests that particles falling into a black hole might remain entangled with particles outside the event horizon, creating connections that persist even across the boundary where space and time cease to have familiar meaning. These quantum correlations might be the key to understanding how information is preserved when matter falls into black holes, resolving paradoxes that have puzzled physicists for decades. As astronomical observations become more sophisticated, scientists are beginning to search for signatures of cosmic entanglement in the structure of the universe itself. They look for patterns in the distribution of galaxies, correlations in the properties of distant quasars, and subtle effects in the polarization of light from the cosmic microwave background that might reveal the quantum scaffolding upon which the visible universe is built. The possibility of cosmic-scale entanglement also raises profound questions about the nature of time and causality on universal scales. If quantum correlations can persist across cosmic distances and billions of years, what does this mean for our understanding of cause and effect in an expanding universe? Perhaps events that appear causally disconnected by the light speed limit are actually connected through quantum channels that operate outside the familiar framework of space-time. These cosmic connections might also influence the evolution of complexity in the universe. The formation of stars, the synthesis of heavy elements, the emergence of planetary systems, and even the development of life might be guided by quantum correlations that ensure the universe evolves toward greater complexity and organization. The apparent fine-tuning of physical constants that makes life possible might reflect an underlying quantum connectivity that coordinates the behavior of matter and energy across all scales. As you drift deeper into contemplation of this cosmic web, you might feel both humbled and comforted by the possibility that you are intimately connected to everything that has ever existed or ever will exist. The quantum entanglement that creates such wonder in our laboratories might be the echo of connections that bind you to distant stars, ancient supernovae, and perhaps even to forms of consciousness that have emerged elsewhere in this vast, interconnected cosmos. But if quantum entanglement operates across such cosmic scales and billions of years, what might this reveal about the nature of time itself, and whether the distinction between past, present, and future might be as illusory as the apparent separation between entangled particles in our earthly laboratories? In the gentle twilight between waking and dreaming, where thoughts flow like water through the landscape of consciousness, imagine time not as the steady march of moments you experience in daily life, but as something far more fluid and mysterious. If quantum entanglement can transcend the boundaries of space, connecting particles across vast distances in ways that seem to mock our understanding of separation, what might it reveal about the nature of time itself, that other fundamental dimension that shapes our experience of existence? Traditional physics treats time like a river flowing in one direction, carrying events from past through present toward future in an orderly progression that preserves cause and effect. But in the quantum realm where our entangled particles dance their mysterious ballet, this linear flow begins to blur and eddy in ways that suggest time might be far more flexible than our everyday experience indicates. Perhaps the instantaneous correlations we observe between entangled particles are not violations of time's order but glimpses of a deeper temporal reality where past, present, and future exist simultaneously. Consider the delayed choice quantum eraser experiments, those mind-bending investigations where scientists can seemingly change the past behavior of photons by making measurements in the present. In these experiments, entangled photons are separated, with one traveling a longer path than the other. The photon that arrives first creates a pattern that depends on whether its delayed twin will be measured in a way that preserves or destroys quantum information. It's as if the future measurement reaches backward through time to influence the pattern created by the photon that has already arrived, suggesting that the quantum present extends both backward and forward, encompassing what we normally think of as separate moments. This temporal non-locality mirrors the spatial non-locality of quantum entanglement, hinting that just as particles can be connected across space, events might be connected across time in ways that transcend our linear understanding of causation. The measurement you make now on an entangled particle doesn't just affect its distant partner in space, it might also influence the entire history of how that entanglement came to be, weaving present choice into past reality in ways that make the distinction between cause and effect as fluid as the quantum states themselves. In the mathematics of quantum mechanics, time appears not as a fundamental flow but as a parameter, a coordinate that can be manipulated and transformed just like the spatial dimensions. Quantum systems can exist in superpositions not just of different positions or properties but of different times, holding multiple temporal possibilities in suspension until measurement collapses them into a single classical timeline. This suggests that what we experience as the present moment might be just one facet of a more complex temporal crystal where all moments exist simultaneously. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no explicit time parameter at all. In this view, the universe exists in a timeless quantum superposition encompassing all possible histories simultaneously. What we experience as the flow of time emerges from the entanglement between different parts of this cosmic quantum state, like individual notes emerging from a symphony that contains all music ever written or ever to be written. This timeless perspective on quantum reality suggests that the past you remember, the present you experience, and the future you anticipate might all be equally real, existing simultaneously in the quantum substrate that underlies classical space-time. Your consciousness moves through this temporal landscape like a spotlight illuminating different moments, creating the illusion of flow while the entire temporal symphony plays eternally in the quantum background. Entangled particles seem to inhabit this eternal now, their correlations existing outside the usual constraints of temporal sequence. When you measure one particle and find it spinning clockwise, its distant partner immediately assumes counterclockwise spin, not because information traveled from present to present, but because both measurements were always correlated in the timeless quantum state that underlies the apparent temporal separation of the measurement events. Some physicists speculate that consciousness itself might be a quantum phenomenon that transcends the usual limitations of time, creating the subjective experience of flow through the careful orchestration of quantum entanglement in the brain. If thoughts emerge from quantum correlations among neural microtubules, then consciousness might have access to information from multiple temporal states simultaneously, explaining phenomena like intuition, creativity, and the strange way that solutions to problems sometimes seem to arrive from the future. The implications extend beyond individual consciousness to the possibility of retrocausality, the idea that future events can influence past ones through quantum channels that operate outside the classical causal structure. This doesn't violate the fundamental laws of physics because no classical information travels backward in time, but quantum correlations can create patterns that link future choices with past events in ways that make the entire sequence appear to unfold as a single, temporally extended quantum event. This quantum view of time also offers new perspectives on memory and anticipation. Perhaps memory is not just the storage of information about past events but a quantum correlation with earlier states of the universal wave function. Similarly, anticipation might involve quantum entanglement with future possibilities, allowing consciousness to sample potential futures and prepare for the most likely outcomes. The uncertainty you feel about future events might reflect the quantum superposition of multiple temporal possibilities, all equally real until the moment when present observation collapses them into a single experience timeline. The delayed choice experiment suggests that the universe might maintain quantum coherence across time scales far longer than previously imagined, preserving entanglement between past and future events in ways that challenge our understanding of temporal causation. If quantum correlations can persist across billions of years of cosmic expansion, they might also persist across the temporal dimension, creating connections between events separated by vast spans of time. As you contemplate these mysteries of quantum time, you might feel a sense of peace in recognizing that the anxieties and regrets that tie you to past and future might be based on an incomplete understanding of temporality itself. If all moments exist simultaneously in the quantum foundation of reality, then the present moment is not a fleeting transition between non-existent past and future but a window into the eternal now that contains all possibilities, all experiences, all potential forms of existence. The meditation on quantum time reveals that the flow you experience might be not the fundamental nature of time but the particular way consciousness navigates through a temporally extended quantum state. Like a reader moving through a book where all pages exist simultaneously, your awareness creates the experience of sequence and flow while moving through a story that exists complete and eternal in the quantum library of all possible histories. This understanding transforms the nature of choice and responsibility. If future possibilities exist in quantum superposition, then every decision you make might be less about creating new realities and more about selecting which of the already existing quantum possibilities will become your experience timeline. The weight of choice remains, but it's accompanied by the comfort of knowing that all possibilities exist simultaneously in the infinite creativity of quantum time. The particles in our laboratories continue to demonstrate these temporal mysteries, their entangled states existing in the eternal quantum now while their measurements create the classical illusion of temporal sequence. They teach us that time, like space, might be an emergent property of deeper quantum relationships rather than a fundamental feature of reality itself. As we prepare to conclude our journey through the quantum landscape of entanglement and connection, we find ourselves approaching the deepest questions of all, not just what quantum mechanics tells us about particles and forces, but what it reveals about the relationship between consciousness and cosmos, between the human desire for meaning and the universe's apparent abundance of mystery and beauty. In the quiet spaces where science meets philosophy, where mathematical equations dissolve into wonder and precise measurements give way to profound questions about the nature of existence itself, quantum entanglement whispers ancient truths that humanity has always sensed but never quite proven. The invisible bonds between particles that we've explored through these chapters echo insights that mystics and philosophers have proclaimed for millennia, that separation is an illusion, that all things are intimately connected, that the universe is not a collection of isolated objects but a single, breathing whole. Long before scientists discovered entangled particles in their laboratories, the ancient Chinese spoke of the Tao, the invisible force that connects all things in perfect harmony. Hindu philosophy described Brahman, the underlying unity that manifests as apparent multiplicity, where individual consciousness discovers itself to be one with universal consciousness. Buddhist teachers pointed to the interdependence of all phenomena, suggesting that what we perceive as separate entities are actually facets of a deeper, interconnected reality that transcends the boundaries created by conceptual thought. Now quantum mechanics provides a scientific framework for understanding these ancient insights, not as mere poetry or wishful thinking, but as precise descriptions of how reality actually operates at its most fundamental level. The entangled particles dancing in our laboratories serve as ambassadors from a realm where the mystical and the measurable converge, where spiritual intuition finds validation in mathematical precision, where the deepest truths about existence reveal themselves through careful observation and rigorous experimentation. This convergence invites us to reconsider the relationship between scientific discovery and spiritual wisdom. Perhaps the greatest scientists throughout history have been successful not just because of their analytical abilities, but because they possessed a deep intuitive understanding of the universe's interconnected nature. Einstein's insights into relativity emerged from his ability to imagine riding alongside beams of light. Newton's laws of motion reflected his intuitive grasp of the hidden harmonies that govern planetary motion. And the founders of quantum mechanics, Heisenberg, Schrödinger, Bohr, all struggled with philosophical questions about consciousness, reality, and the relationship between observer and observed. Quantum entanglement suggests that the boundaries we draw between self and world, between observer and observed, between mind and matter, might be convenient fictions that help us navigate daily life but obscure deeper truths about the nature of existence. When particles can share instantaneous correlations across vast distances, when measurement creates rather than merely reveals reality, when consciousness appears to play a fundamental role in determining what becomes actual from the realm of quantum possibilities, the rigid separations of classical physics dissolve into something far more fluid and mysterious. The philosophical implications ripple through every aspect of human experience. If quantum entanglement operates at the cosmic scale we explored, then your consciousness might be intimately connected with the consciousness of every other being, every distant star, every galaxy spinning in the cosmic web. The loneliness and isolation that sometimes shadow human experience might be artifacts of a limited perspective that hasn't yet recognized the quantum threads connecting all things in an invisible tapestry of relationship and correlation. This understanding transforms the nature of empathy and compassion from mere emotional responses to recognition of literal truth. When you feel connected to another person, when you sense their joy or suffering as if it were your own, you might be experiencing the quantum entanglement that links all conscious beings at levels deeper than individual identity. The golden rule, treating others as you would wish to be treated, becomes not just moral guidance but recognition of the underlying unity that makes self and other aspects of a single, interconnected reality. The quantum perspective also offers new ways of understanding creativity and intuition. If consciousness can access quantum superpositions that contain multiple possibilities simultaneously, then creative inspiration might involve sampling potential futures, exploring solutions that don't yet exist in classical reality but await discovery in the quantum realm of infinite possibility. The sudden insights that seem to arise from nowhere, the solutions that appear in dreams or moments of relaxation, might represent consciousness tapping into quantum information that transcends the linear thinking of everyday awareness. Even the experience of beauty finds new meaning in quantum philosophy. The aesthetic sense that recognizes harmony, proportion, and elegance in nature might be consciousness responding to the underlying quantum order that creates apparent chaos from deeper patterns of connection and correlation. When you feel moved by a sunset, a piece of music, or a mathematical equation, you might be experiencing resonance with the quantum symphony that orchestrates all existence. The study of quantum entanglement also illuminates the nature of knowledge itself. Classical science assumed that objective reality existed independently of observation, waiting to be discovered by neutral observers who could study the universe without affecting it. But quantum mechanics reveals that knowledge is participatory. We cannot know without changing, cannot observe without influencing, cannot separate the knower from the known. This transforms science from a detached study of external objects into an intimate dialogue between consciousness and cosmos. This participatory universe invites a new kind of humility before the mystery of existence. If reality is fundamentally quantum, then uncertainty is not a limitation of our knowledge but a feature of reality itself. The universe maintains an essential creativity, an openness to novelty and surprise that keeps existence from becoming deterministic and predictable. Mystery is not the enemy of understanding but its eternal dance partner, ensuring that no matter how much we learn, there will always be new depths to explore. The philosophical journey through quantum entanglement also reveals the profound democracy of existence. Every particle, no matter how small, participates equally in the quantum web of connection. Every measurement, no matter how simple, contributes to the ongoing creation of reality. Every conscious moment, no matter how ordinary, represents the universe becoming aware of itself through the lens of individual experience. You are not a separate observer studying an external world but the cosmos knowing itself through your particular perspective. As you rest in this recognition of fundamental interconnection, you might feel both the weight and the lightness of existing as a conscious being in a quantum universe. The weight comes from recognizing that every choice, every thought, every moment of awareness participates in the ongoing creation of reality. The lightness comes from realizing that you are not alone, not separate, not isolated in a hostile cosmos, but intimately connected with everything that has ever existed or ever will exist through invisible bonds that transcend space, time, and the apparent boundaries of individual identity. The ancient wisdom traditions and modern quantum mechanics converge on a single, transformative insight: the universe is not a machine but a living system, not a collection of separate objects but a unified field of consciousness and possibility, not a stage where isolated actors play out predetermined roles but a collaborative creation where every participant contributes to the ongoing symphony of existence. As we prepare to close this exploration of quantum entanglement and its implications for understanding reality, consciousness, and connection, we find ourselves approaching the most intimate question of all: how these profound discoveries about the nature of existence might transform the way we experience the simple miracle of being alive, aware, and connected in this vast, mysterious, and ultimately loving universe. You find yourself at the edge of wakefulness now, standing at the threshold between the quantum world we've explored together and the dreaming mind that awaits you. The particles that dance through our journey, those tiny messengers of light and matter, they don't simply disappear when you close your eyes. They continue their eternal dance, weaving through your being, connecting you to everything that has ever been or ever will be. Think of your body as a constellation of quantum activity. Every breath you take draws in atoms that were once part of distant stars, ancient oceans, the first flowers that bloomed on Earth. These particles carry within them the memory of their journeys, and now they become part of your story. As you breathe slowly, deeply, you're participating in the same quantum choreography that governs galaxies spinning in the cosmic dark and electrons orbiting in the spaces between your thoughts. The electrons in your neurons are preparing for sleep, their quantum states shifting like tides responding to an invisible moon. They don't rest the way you might imagine, instead, they enter a different kind of dance, one that allows your conscious mind to step back while deeper processes take the stage. In this quantum realm of sleep, your brain becomes a theater where memories reorganize themselves, where the day's experiences are woven into the larger tapestry of who you are becoming. Scientists have discovered that during sleep, your neurons fire in synchronized waves, creating patterns that ripple through your brain like gentle quantum currents. These waves carry information from one region to another, consolidating memories, processing emotions, and perhaps, just perhaps, touching something larger than individual consciousness. The quantum field that connects all particles doesn't recognize the boundaries we imagine between self and other, between dreamer and dream. As your eyelids grow heavy, photons from the last light you see continue their quantum journey through your visual system. They become electrical signals that travel along neural pathways, each pulse a quantum event that transforms light into thought, sensation into memory. Even in darkness, this quantum processing continues, creating the inner landscapes of dreams from the same fundamental forces that shape reality itself. Your heart beats in its steady rhythm, and with each pulse, trillions of quantum interactions coordinate the flow of life through your body. The hemoglobin molecules in your blood carry oxygen through quantum mechanical processes that scientists are still discovering. Each oxygen molecule finds its destination through a kind of quantum navigation system, guided by forces that operate faster than light and beyond the reach of classical physics. The boundary between your dreaming mind and the quantum field becomes beautifully blurred in sleep. Just as particles can exist in multiple states simultaneously until observed, your dreaming consciousness experiences multiple realities, multiple possibilities. In dreams, you might fly or find yourself in impossible places, and perhaps this isn't so different from the quantum superposition that allows particles to be in many places at once. Consider the mystery of how your sleeping brain continues to monitor your environment, ready to wake you if needed, while simultaneously creating rich dream worlds that feel completely real. This suggests that consciousness itself might operate according to quantum principles, existing in multiple states, processing multiple streams of reality simultaneously. Your sleeping mind becomes a quantum computer of sorts, exploring possibilities that your waking consciousness might never consider. The atoms in your pillow, your blanket, the air around you, they're all participating in the same quantum dance. Temperature itself is just the average motion of quantum particles, and as your body temperature drops slightly in preparation for deep sleep, you're experiencing a quantum mechanical process. The warmth that radiates from your skin carries photons into the darkness, connecting you energetically to everything around you. Even the silence of night isn't truly silent. At the quantum level, the vacuum of space buzzes with virtual particles popping into and out of existence, creating what physicists call zero-point energy. This quantum foam underlies all of reality, including the space between your thoughts as you drift toward sleep. You're never truly alone because you're always embedded in this field of quantum activity that connects all things. Your dreams tonight might take you to distant places or impossible scenarios, and in the quantum world, distance and impossibility have different meanings. Particles can tunnel through barriers that should be impenetrable, appear instantly in locations far from where they started, and influence each other across vast spaces. Your dreaming mind, freed from the logical constraints of waking consciousness, might be tapping into these quantum possibilities. The memories that surface in your dreams, fragments of conversations, faces from long ago, emotions attached to moments you thought forgotten, they are stored in quantum patterns in your neural networks. As you sleep, these patterns reorganize themselves, creating new connections and insights. The creative solutions that sometimes appear in dreams might emerge from quantum processes that allow your brain to explore multiple solution paths simultaneously. As sleep deepens, your brain waves slow into delta rhythms, long, rolling patterns that coordinate across millions of neurons. These synchronized oscillations might be your brain's way of accessing quantum coherent states, moments when individual neural activities align into something larger than their sum. In these moments, the boundaries between separate thoughts, separate memories, separate aspects of self become as fluid as the boundaries between quantum particles. The darkness behind your closed eyelids isn't empty, it's full of potential, like the quantum vacuum that holds infinite possibilities until they collapse into reality through observation. Your dreams will select from this vast field of potential experiences, creating temporary realities that dissolve and reform like quantum states responding to measurement. Each dream image, each dream emotion, emerges from the same creative force that brings particles into existence from the quantum foam. Tonight, as you surrender to sleep, you join the eternal quantum dance that connects all conscious beings across space and time. The particles that make up your body have been part of countless other forms of life, other dreamers, other moments of awareness throughout cosmic history. In sleep, perhaps you touch the same timeless awareness that guides quantum particles in their perfect choreography, the same intelligence that orchestrates the dance of atoms and stars. And as consciousness fades into the quantum mystery of sleep, you carry with you the wonder of knowing that you are not separate from the universe, you are the universe experiencing itself through the miracle of awareness, about to dream new worlds into being.